basically, the math is basically the same. So instead of a gamma p, now we have a gamma w. So gamma now is basis functions instead of known nonlinear functions. So basis functions, you could have like Fourier series, you could have splines, but those aren't usually called neural networks. But you could use Gaussians. If you use Gaussians, that is called a neural network. And yeah, so W now is weights rather than parameter estimates. So I mean, the parameter estimates, we kind of know that there are ideal values for the parameter estimates. Like, we know we couldn't actually estimate them accurately, but we know that real values for them exist. The weights is a little different. Like, what are the, you know, there might be a set of ideal weights, but even how do you define those? So you don't really know what the correct weights are anymore. But so it's a little bit different conceptually, but the math is kind of identical. So why would you use neural networks? Well, one thing might happen is that you don't have something that's linear in its parameters. Now with the robot we did so far, the rigid robot, there's actually no problem doing adaptive control. So you don't have to do neural networks for the rigid robot. Because all those dynamics in the rigid robot, the inertia matrix, Coriolis and centripetal terms, damping, gravity, all those nonlinearities were linear in their parameters. All those things in the robot had a parameter multiplied by a nonlinear function. So you could easily do adaptive control for the rigid robot. But there are some control methods out there where you do have to take M inverse. You have to invert the inertia matrix. And if you have a control method that you need the inverse of the inertia matrix, the inverse of the inertia matrix is not linear in its parameters. And then you would have to use a neural network. Now when we talk about the flexible joint robot, so hopefully everyone's busy turning their rigid robot into a flexible joint robot in the last few weeks, and show us the results on November 6th. In that case, you'll find it's a real pain to try and do parameter adaptive control with parameters, because you get like, I don't know, 1 billion parameters? No, not literally 1 billion, but hundreds at least, hundreds of parameters. And in adaptive control, you know, P, when I write an update saying P hat died, I'm definitely implying that you have to integrate, right? So you're gonna have to call an integrator to integrate all those hundreds of parameter estimates for your flexible joint robot. That's a little unreasonable to do in real time. You can hook up, imagine going into MATLAB and Simulink file and hooking up a 1/s block in Simulink and then typing in it has 300 inputs into it. Imagine how fast that's going to run. Not very fast. So a big advantage of using neural networks is you can use a delta rule, which, I mean, is integration. It's just rectangular integration, right? It's integrating with rectangles. But anyway, a delta rule, super easy to update. You can just update it at your control frequency in discrete time. And then it becomes very reasonable to apply all your parameter updates to the neural network. So I guess I should really write delta W here, right? Delta W. So let's just talk about the simplest kind of neural network first, which is radial basis function network. So for one input, you would have gamma of x is equal to e to the negative x minus c, or gamma I of x minus ci squared over sigma squared. So you basically just have a bunch of Gaussians. and sigma is a positive constant. So the reason I use sigma squared here is because that's what you would see in like a bell curve, and then sigma would be like the standard deviation. So I think it's just a little more intuitively obvious what sigma signifies when you think in terms of standard deviations. If I write sigma squared there, we kind of have some intuitive understanding of that already. So for n inputs, so hopefully that's pretty obvious. Anyway, I'll give you some computer code for this, and you don't really have to figure it out yourself, but that's pretty straightforward, right? And if we were to talk in terms of multiple outputs, so that's for multiple inputs. For multiple outputs, what we can do is basically use the same basis functions, just different weights. So mathematically, we should show how to show that. So for multiple outputs, probably the way I would set it up. These lines, a lot of zeros everywhere, multiplied by my weights. That's not the only way to do it. I could reverse it so that my basis functions are in the vector, my weights are in the matrix. That's also some way people write it. So basically, in shorthand, I would just write this. So essentially it still looks the same mathematically as I did for the adaptive control. So let's just do an example. like I said, these could be any, really these could be any basis functions. Fourier series or splines or whatever you want. But Gaussians are by far the easiest to deal with in terms of multiple dimensions. Splines and Fourier series are fine with one dimension, probably maybe better than Gaussians. As soon as you get into 2 or 3 dimensions, maybe you want to use Gaussians because they're just way more computationally efficient. So, does everyone have all this messy matrix?
Not that one thing, right?
So let's just do an example. Radial basis function network. This is probably a terrible example because obviously you could use normal adaptive control here. You just have an adaptive parameter for A and an adaptive parameter for B because in this case is linear in its parameters. But anyway, this will illustrate the method. And so remember, for this kind of system, I'm probably going to use one of these sliding mode auxiliary error things to do it. Just like I did for the robot. About that. And then I have W tilde equals W minus W hat, where W are the ideal weights. So my ideal weights are really unknown and maybe even unknowable. And I don't even really know what I mean by the word ideal. So basically some constant set of weights that would be good, I guess. W hat are the weight estimates. But these are the actual weights, even though I call them estimates. So that's what I actually have in my neural network. So V dot is equal to, I'm going to use V is equal to 1 over 2G Z squared plus 1 over 2 beta W tilde transpose W tilde. And I am making things a little bit easier for this example by assuming I know what G is. I can deal with an unknown G, it's just a bit more complicated, so I don't want to introduce it right away. Let's just keep with a simple example to teach you the techniques. I forgot my Z here. And that should be a minus sign here. Sorry. E dot is equal to Z gamma W plus D of X plus U plus theta D over G minus 1 over B. Okay. So what I used here, I used the fact that F of X is equal to gamma of X W plus D of X for all X in D. Okay, so in this case, when I wrote in my previous example, when I was talking about introducing like a disturbance d of x into the equation here, what it was external disturbances. So little things in the real world that might affect the system, which I didn't take it into account when I first did the adaptive control derivation. But now I get a d of x in here because I want to estimate this function f of x with this basis functions times the weights. But when I do that, I'm not going to get an exact approximation. So it was a little bit different when I had a nonlinearity that was linear in its parameters. Then, the gamma p would be exactly equal to f. But in this case, using basis functions, I get a little bit of an approximation error. So d of x is the approximation error of the neural network. So the idea here is that if I pick enough basis functions, then I will have a d of x that's bounded by some positive constant d max in my region D. Okay? So if I don't pick enough basis functions, this won't be true. So if I'm trying to model x squared and I'm using 1 Gaussian, it's not even close, right? I mean, it's not even going to be in the same ballpark. But as long as I use enough Gaussians with enough, spread out enough, then I'll be able to uniformly approximate that nonlinear function. Okay? So what we say is that RBFN uniformly approximates f of x, okay? Or is capable of uniform approximation anyway. So then I have E dot is equal to Z gamma W hat plus D of X plus U minus theta double dot D over G plus W tilde transpose gamma transpose Z minus W hat dot over beta. And so now it kind of is exactly the same as my adaptive control. So I'm not writing down anything really different than I did before, other than that P becomes W now. And let's pick E modification as my robust weight update. So notice in this case, I need a robust weight update even in computer simulation. With the adaptive control, I didn't have to have the robust update on my computer simulation, just when I implemented it in real life. Now I'll even need it even in computer simulation, or else my computer simulation will go unstable, because that little d of x approximation error in there. So I get B dot is equal to Z transpose D of X minus KZ plus nu Z W tilde transpose to B hat, which I already found, or already proved, is uniformly ultimately bounded. So I already did that mathematical analysis for that, I don't have to do it again. So well, let's actually take a look at this computer simulation, see what it looks like. Okay, so I have a desired trajectory here. I have a desired position, velocity, and acceleration coming into the left here. That's going into my controller. So my controller is just exactly what I wrote on the board there. And that's going into my AX8 times cos minus B times X2 plus GU. Integrate to get my X2. And then X1 dot equals X2. So integrate again to get my X1 position. So it's pretty simple. The control is, so I want to set up my, the first thing I do in the code is if you look through the code, the first thing I do is initialize the radial basis functions. So that's just choosing basically some centers for my Gaussians. So I'm just choosing my Gaussian centers on a lattice, on a grid. I mean, there's various ways I could choose them. I could just randomly pick them for random numbers. But it kind of makes more sense to pick them on a grid, I think. And you do have to establish your zone. Like, we're using this, I said that it has to approximate the nonlinear function in D. So there's going to be some region D that you're going to have to define, saying, I'm going to work within this region. So you're going to have a minimum and a maximum expected input for each of your inputs, right? So you're kind of defining the region where the neural network is going to approximate the nonlinear function. And I wrote up weight updates, but I never said what the initial condition was. So it makes sense just to have the initial condition be 0 usually, unless there's some real need for you to have. I mean, sometimes you have to have, at least a constant value to start off with. But often you can get away with just setting all your weights to 0 to begin with. And so essentially the system knows nothing about your system. I mean, you could try and do some pre-training too, kind of train your neural network if you knew something about your system and kind of train it approximately before you started the adaptive process. But there's no problem with starting everything at 0. And then in the control itself, I'm just going through and finding out what the value of all these Gaussians are. And one little trick I do that I didn't write on the board is that I normalize them. So that usually helps. So not just Gaussians, but they're normalized Gaussians. So I just divide by the sum of all the Gaussians, and that gives me a bit better basis function when I normalize. Okay. And when I normalize, this becomes equivalent to a fuzzy logic system, and every Gaussian can be thought of as a fuzzy membership function with a truth value between 0 and 1. So that's kind of the other advantage of normalizing. And then, so I'm just applying this control. The output 1 is the output for my neural network. And I have this other term that depends on my desired velocity. Like I said, there's no problem. You can redesign this. This is actually, in my notes, my notes this was G, not C, but in the code it's C. But if that's not known either, you can redesign this to, I mean, you could just have an adaptive parameter for C. That would probably be the easiest thing to do. You don't need a neural network to estimate a number as overkill. So I could just use a parameter, adaptive parameter estimate to estimate C if I didn't know it. And so this is the big advantage here, is that I'm just applying basically a rectangular integration, so a delta rule to do my weight update. So I'm not integrating these weight updates. So notice, if I was setting up, you know, my update of the weights occur inside the control. So if I was doing an adaptive control with parameters that I was updating, then I would have another 1 over S block here, and I would have to output all my adaptive parameters into my 1 over S block and integrate all my parameter estimates. And like I said, there could be like hundreds quite easily for something like a flexible joint robot, so you might get into trouble really quick. Although with a rigid robot, it'll probably work fine, because you probably only have like maybe like 20 or 30 adaptive parameters in the rigid robot, so it'd probably work fine for the rigid robot. So this is kind of the big advantage, is that I can just apply this delta rule here to do the updates in the neural network. As far as I know, I'm the only one in the literature who wrote some papers kind of showing why you can use the delta rule and you don't have to actually integrate. But as far as I know, everybody actually does that in real life. So, does anyone have any questions about this, using radial basis functions and adaptive control? Anyone have any questions about this example before I guess I should run it for you, see what it does. So these are my weights. I didn't run it quite long enough for my weights to converge, so don't do this when you hand in your project. So make sure you run it long enough for your weights to converge or your adaptive parameters to actually converge. But you do, the big thing is to make sure that they're not actually growing. So I'm not too worried here. They're decreasing. That looks pretty good. So I think they're going to decrease and then converge to a constant value or an oscillating value. That's fine, as long as they're not going up. So if they're going up, then I'd be very concerned that I didn't design my robust update properly. Okay? So very important to show this kind of graph when you do your project so we can confirm that your system's stable. As far as the performance goes, if I zoomed in right at the beginning, you can see that there's a little bit of error at the beginning. So this is kind of the training phase of the neural network, if you will. And then, but by the second time it's done it, it's almost perfect. And by the third time, it's essentially perfect. So it doesn't take a lot of training in the sense of neural, like often we kind of think of neural networks as training over a large amount of data for a large amount of time before they can do anything useful. So when you throw them into an adaptive context like this, they're actually pretty much useful right away. So if you're comparing this to like a PID control for the system, so if you had a well-tuned PID control, then for that first oscillation there, the PID control might outperform the RBF network, or it might not, but you might do worse here than the PID control on the very first time. But by the second time, there's no way that the PID would do better than that. So it would already outperform a PID even by the second time it was doing a trajectory. Because that integral term is going to introduces a bit of a lag in there. It can't follow this kind of trajectory perfectly, right? So it would definitely outperform the PID even by the second oscillation here of the trajectory. Any questions on this example? Yeah.
Just generally on neural networks. So we had a disturbance term. Well, we had a dx term, but that was really for the approximate error. Did we ever take into account external disturbances?
Yeah. So if there's external disturbances in your system, they'll just show up in that exact same term. So the math will look the same. It's just that d of x will include both neural network error and external disturbances. In which case it might become a d of x and t rather than just d of x, because the external disturbances might depend on time. But otherwise, the math stays the same, and it's the same idea. Then d max, you have to have a d max that includes both your neural network error and any external disturbance terms.
And then you would probably just see, like, if you had external disturbance on this, it might take longer to learn, or if you had the external disturbance comp, it would diverge and converge again.
If the external disturbance was big enough, it could prevent the error from going as close to zero as you see going now. Like it'll adapt to, and it'll kind of learn an external disturbance. So if the external disturbance was like predictable, like it was just sine t, then they would actually learn that right away, and then you wouldn't see any effect from the external disturbance. The only time the external disturbance is going to affect the error is if it's kind of unpredictable, and the neural network can't actually learn it. So for instance, if it was a constant too, it would just automatically adapt for it right away. So you wouldn't even really notice it. It's only if it was kind of like some kind of random disturbance that it would really affect the error. Any other questions? So this code is up on D12 for you to play with if you want. So when would you use radial basis functions? So basically you would use radial basis functions when your number of inputs is probably less than 5.